So, good morning, friend. Today we are into our second week. So, let us understand the taxonomy of what we are doing. This indicates week 2, lecture 1. You can so it will help you in organizing your studies and schedules. And then if you look at the title, we have AI, ML, artificial intelligence and machine learning. Of course, deep learning is part of it. Enabled reliability assurance. In fact, it is a sort of new paradigm. That means AI, ML is translating or bringing a paradigm shift into what we used to think about reliability as a probabilistic notion. Now, here in this lecture, we are bringing the failure instant of failure. So, from that point of view, it's a new technology that is developing, and of course, in elite industrial houses, it has become part of it, at least for the critical systems, and in other industries also, when a full potential of this is realized, because now we are not talking of a probability of failure, we are talking about instant of failure. Probability can be 10 to the power minus let's say 3, but then it could be tomorrow, or it could be after 1 year, or it could be after 6 months. But here we are focusing on reliability assurance, and this is very useful for operation maintenance ecosystem, because the moment you know that this component is going to fail in next 6 months, next 10 days, next 10 hours, it helps the industries to prepare for the prognostics, the operation management initiative, so that the consequences of failure can be either eliminated or can be reduced to an acceptable level. Okay. So, this is the thing, and in last lecture we had this introduction about this whole area, whether we call prognostics health management, and how we are trying to realize PHM for systems approach. Traditionally, people talk about the failure mode effect and criticality analysis and all that, but now here we are bringing in a probabilistic risk assessment concept, which is an integrated model of the system, where common cause failure, which is one of the more desirable thing to be addressed with appropriate attention. So, that kind of thing. Of course, in plant there are defenses against common cause failures and all that, but then you can imagine one event, a single cause, and can disable the whole safety, you can say, barrier, because the 3 redundant component, they were operating on the same principles, and if one event like increase in humidity, flooding of the area, or many other things, and as I said, there are defenses in the plant, but common cause failure still remains one of the critical factor in safety or risk assessment. So, let us see what is there in the offering in this lecture, as well as in the during the week. So, Salient features, I have talked about it, instant of failure, PHM. It has potential to change the paradigm or bring a paradigm shift into maintenance and operation management strategy, because not only remaining useful life, it is enabling a management approach also in the operation system. So, it is touching the both the areas. So, the moment I say operation, it is operation and maintenance, or if I say maintenance, operation is inherently part of it. So, week 1 overview I have given you, that we have introduced prognostics and health management as a tool, and how a systems approach, it has been just brought in that element in a very simplified form, so that in first lecture itself you realize or you can understand the scope of this particular lecture. And then specific requirements of systems approach. In fact, through once this lecture, this course is over, you will know that now you understand the system also, you understand the maintenance also, you understand the operation also, not only normal system but safety critical systems. So, that is one of the biggest takeaway from this lecture. And concept of life consumption. life consumption concept, the roots are there long ago, but then not much work was done. But now we are demonstrating that the remaining useful life can be monitored, either through sensor or through physics of failure model or a canary-based approach, and that we are going to see in the lecture how we do it actually. Role of sensor systems, data acquisition system and devices and network. Probably this will have some discussion, but it will be just one slide. It will tell you how we are achieving our PHM in its in holistic form. Then higher level specification requirement, and then AI ML enabled prediction capabilities and uncertainty management. It is very important that it is difficult, or it is almost like a impossible task to tell the instant of failure in a very precisely. So that's why the uncertainty statement has come. So it will tell you within one uncertainty band. If you are talking about remaining useful life to be 10 hours, so it can be there that 9 hours to 11 hours, and that is pretty understandable. Okay, and that's how the program is here. And now we have this. PHM has potential for instant of failure. I told you it is focusing on instant of failure and along with the uncertainty statement. So that makes this statement of instant of failure more holistic and acceptable in engineering parlance actually. The R&D data, still lot of R&D is going on. In fact, PHM, a good part of it is in the R&D stage in elite labs. And that is where there is a potential to bring it into the system. For advanced system, it has already been there in a limited way, and now the idea is through this lecture and many labs are working in India, they want to bring it very close to the real-time application. Like for example, railways may be interested in implementing prognostics and health management program, even though bearings are supposed to be most reliable component, but the number of bearings are so much, there is a 35% failures are attributed to the bearing. So because one coach has almost like 30 to 50 bearings operating contiguously, whether it is axle bearing, traction motor, or so these type of industries, they are critical industries. They are basically mission bound industries, and safety is an overriding factor. So these industries, they need it to address safety as well as reliability both. And now reliability means in the context of remaining useful life. And of course, probabilistic notion will help and all. Here we don't mean to say that reliability is going out of the window. Uncertainty characterization is done through statistical and probabilistic approaches. So that component is already there, and it is inevitable as long as randomness is there in the system operation, design, maintenance. So it remains a part. But now we are talking about seeing the reliability in different perspective, that is instant of failure. And systems approach, yes, because traditionally the PHM approach has been dealing with a component level or structure level, be it them is a mega component or structure, or some component like pump, electronic card. So it was going for component specific, or so now we are talking about the system. So when you do it for the system, probably when you address 20% of the component, 80% of the risk, reliability or safety issues are addressed, and that is a good incentive to work on this area. And one more important thing is when I talk about that human contribution, most of the accident, if you see, human contribution form part of it. From the contribution can range from 70% to 80%. Somewhere in the accident sequence, at least one event will be there, which is attributed to human failure. So now, why not, when we do for hardware component, why not for human prognostics? So for all my researchers, human prognostics is one of the area, and of course, in my book, I have initiated this thing so that we can tell a priori, okay, what can be improved, whether we can improve the training program that we are responsible for certain thing, or we can have the cognition coefficient increase, so that and there are many methods to do that, and so that will be prognostic. Human prognostics is, I would say, since prognostic itself has emerged, our inspiration in prognostics and health management is there from the medical field or healthcare. And now again when we talk about in engineering human prognostics, it is basically we are forming a closed loop, and there is a need to start research in this, and this is where I leave it. Maybe one or two more slides I'll show there on this. Now let us understand the terminology which are associated with the subject that we are dealing in. Prognostics. Prognostics is basically prediction. Prediction of essentially, if you say, remaining useful life, but it can be used in many things. For precursor monitoring, it can be used for which may or may not be a failure, or we are waiting for something and then health management. That means it is a holistic approach. It doesn't remain limited up to you are predicting the failure. It is also linked to the health management. Why? Because we have now remaining time, we know how much time is available with us, and if you can visualize a complex system, a mega system, in which if actions are taken in time, then consequences can be eliminated. So that is so we have a statement of remaining available time also can be derived, considering the job to be done and whether it can be achieved or not. So the 3-4 level of management program can be issued, and the most effective one can be implemented. Now, power of PHM. Power of PHM is, if I have to say one word, it is replacing the probability of failure with the incident of failure as a central element. Okay, and then it has got online monitoring. Let us say I have assurance on day-to-day basis. Failure comes quite late, but I am having assurance online that the system is operating based on the online signatures that are available, and it is a big achievement in terms of seeing that plant is in plant control room. How you know that things are operating smoothly? It is because of there is no signal available and it is peaceful thing. But there are some sort of a latent failure for which we have designed the PHM. There are some catastrophic failure. If we can detect some sort of leakages and all that, probably there will be some information and all that. So keeping those kind of thinking on track, and we can achieve this kind of thing. Now source of power comes from AI/ML. I would say I would give maximum credit to the evolution of artificial intelligence and machine learning approaches. And of course, physics of failure model. So there are 3 approaches: data-driven, physics of failure approach, canary approach, and this canary approach. So, and of course, fusion approach. Fusion approach combines. I will talk about it later on. It combines the data-driven approach and PO approach. Okay. Now, if you see the chronological order of the PHM or diagnostic or prognosis that has been developed by J.B. Coble and all that, I have referred this figure from the literature, and it really, according to me, being a ex-plant operation maintenance personnel, I know it brings in the control room perspective. Because in control room also we get data from the various areas. I am talking about a mega system where the plant itself is spread out into something like a kilometer or maybe 500 meter radius or so, or even it could be from 500 meter to 1 kilometer radius. So data comes to the control room, and we pretty well know things are normal. Then why we know that is normal? Because we monitor the data and detect any deviation if anything is there. And if suppose any deviation is there, then we get into diagnostics, okay, and try to bring the plant to normal, okay. But this particular phase is presently it is not there. If there can be a prognosis, or even if it is there in some way or other, it is in a very primitive stages and all, because we scientifically we don't have a prognosis program, and then so this kind of thing will be maybe another 5 years, 10 years, it will become a regular element, or even industries are even embracing it. As I said, the elite industry, elite labs, they are embracing it, and then planning of activities can be done. So you can see we started with the data and all that, and here also I am trying to see in the text the same thing. I can imagine a control room ecosystem, and that is where if I have a prognostics module, in fact, the technology has pretty well gone into the condition-based maintenance. That means it will tell you the degradation, but it will not be able to predict how much time is there. So which is in we are talking about it. So control room can be characterized by panels spreading into some 10 to 15 meter areas, and then there is a console where you can do plant operation maneuvering and all that. So and then there are human element, that is operators, which are manning the control room and provide surveillance and then take the action. If a prognosis is there, it will be sort of either we do in one shift recovery job, or we do in 1 month, and depending on what kind of prediction has been done and how much time is available. So we are pretty well correlate this whole thing with the plant control room scenario also, how we look at it. Now we are talking about prognostics, but then there is a data acquisition system. And the data acquisition system, when we talk about it, it really is at the core of it on prognostics. So there are two elements. One is sensor, that means selection of sensor and the development of data acquisition system. Otherwise, the prognostics will not be operating the way we want it, and the way we want to have the statement of RUL, okay, and then anomaly detection, okay, and then management module, okay. So here this is a new thing I am introducing. The management component can be done using AI based operator or maintenance support system, okay. When I say operator, maintenance things also come over here. In operation and maintenance, these two agencies in a broad way, they work together and ensure smooth plant operation. So we have this module, and then what we achieve? We achieve, if it is for a process system, we achieve a higher level of reliability assurance. If we achieve safety, yes. And again, one more element that we have to address, and already at international level like IAEA, International Atomic Energy Agency and all, they have started addressing safety and security together. So that means any system built is on today. So my probabilistic risk assessment should address the probabilistic safety assessment and probabilistic security risk assessment. So then only safety assessment will be committed, because at the end of the day we have to keep the plant in a safe state. So both the risk, that is security risk and safety risk, should be addressed, okay. And then based on this we have sensor. In fact, in open literature, if you see FMEECF, failure mode mechanism and effect criticality analysis, this is the tool which is being used for systems approach. But my belief is, if there is a complex system where interactions among the processes, interaction among the component, human interaction, common cause failure, and a common cause failure becoming taking part in the human factor taking part into the common cause failure. This kind of phenomena makes require a PRA framework to understand, analyze and prioritize the systems and component, and have prognostics on those systems on priority basis. And then management online, it goes through the operator advisory system. Here what happened is, rule based approach or even fuzzy based approach can be used to design a framework for diagnostics and action to be taken. And the action to be taken procedures, they come from plant procedures, okay. So we have the stage set for our AI ML module that we have. And as I told you, uncertainty is perform parts of RUL or anomaly detection, which gives confidence. It doesn't take away anything, it gives confidence. Okay, what I am reading, what is the strength of this particular statement, that is RUL. So it's a good thing actually. Okay, then let's go to the root of it. A component has been designed. Its life cycle consumption line has been given, and design severity line is given over here. And we know the failure reference also. Okay, if severity goes to this level, that means stress strength model interference will happen. This will fail. Okay, but this is a design leap. Sometimes it comes as a mean time between failure, mean time to failure, and all that. So, or sometimes it might come in the like nuclear plants. Earlier, it was assumed that the life is 30 to 40 years. Now we realize it is 60 years, and now we are talking about 80 years. So it is an evolving scene. But let us say for this moment, this figure, and we have that if the component, this is our design point we have here based on this study. Now, if the component fails a priori, it has got not only safety but reliability issues and potential risk without monitoring. If we do not monitor it and if it fails, had it monitor, now we get the idea in graphic way. So we have a risk when it is going to fail. If it fails, then if it is a big turbo generator in a power plant, then you can take a couple of days to week also can go, and then it is a financial penalty on the plant. Okay, and if it is fails in a system where there is a demand on safety system, so then safety system may not come on time. So we are not monitoring. But suppose if everything going smooth and the component remains okay even after, because please note that when we talk about the mean time between failure or mean time to failure, we are talking of mu, mean time to failure, mu, So mu is a central line. If you see the normal bathtub curve, 50% of area is there on the right side. Okay, so that means by mean time failure, if somebody says, and if you have to replace when MTTF has reached, then we are losing this much life. Okay, so it is a huge penalty, and it brings in a lot of plant interruption. So the good life of the component we have lost, and probably it is for everyone to imagine depending on their system what kind of compromise has been made. But suppose if I do monitoring, I will know it is up to here, okay, and if even if this situation is there, since I am monitoring, I will know that the signatures are normal and I can keep operating even beyond the design point actually. So this is the advantage. I think in text I am trying to tell the same thing. So it is basically bringing in online monitoring or PHM programs, so importance. Now, we are talking about systems approach where PRA is there, but PRA has given input to risk-based approach, and risk-based approach, so a spin-off is risk-conscious operation management, application of risk-based approach into the operation and maintenance. So, what is how we can see in perspective RCOM and PHM? RCOM consideration is related to after PRA, if you systematic studies and all that, we can see it has got a direct relevance. Because present maintenance strategy are schedule based. So that means when the schedule has arrived or replacement time has come, we replace it either premature or you don't know on time, we don't know actually. And when we talk about the design, if we have a PHM during the design stage itself, there are of course there are even now also the provisions are made for the life limiting component. Provisions are made to see that their degradation in terms of corrosion, in terms of erosion, in terms of many other degradation mechanisms. So but then if we do with these advanced methods, so limiting life will be identified a priori, and there can be whether at regulatory level or at plant level, there will be a comfort level. Okay, you have a lot of margin and all that. And then, so in design itself provision can be made, but in operation there will be huge advantage, which was the work started during design stage considerations, and now we are reaping the benefit in the now system reliability assurance. Yes, there is a direct relevance. Not only safety, we are talking about safety because safety or risk is an overriding parameter, but in terms of reliability also, because this RUL is directly related to the reliability terms actually. Then reduction in risk, yes, it will be there if we have a PHM program, and their trend has already started because now we have in plants a lot of condition based maintenance system, online health monitoring of electronic channel, then online leakage monitoring we have provision. But these provisions comparing with the AI enabled PHM, they are primitive, but they are very elegant also. The moment there is any leakage, it will tell the control room, in this area this is the leakage. So that means you have to take the action. So they are elegant, but if you have to go ahead and take the condition based maintenance approach ahead with more meaningful use, then we have to go for PHM application. Okay. So if you see the overview of this week, we have progressed from introduction to little more intimate concept of prognostics and health management. This concept in some way or other they will keep coming in, and probably we will be revisiting this again and again. It will not be seen as a repetition, but it will be seen highlighting those importance in the context of the presentation that is going on. And the role of data acquisition system we have seen here. A fine, well-balanced data acquisition system is required as a key to implementing the PHM. Role of life consumption monitoring with the graded approach and all, and RCOM and PHM. So they are hand in hand, highlighting through risk-based approach and risk-conscious operation maintenance approach. So RCOM means risk-conscious operation and management approach. So, and this is how we have gone. Now second week onwards, slowly the role of AI ML will be highlighted and all. So with this we complete our presentation, and all of you can go through various aspects, learn more and more, bring in new elements and all. So thank you.